A large rectangular piece of cardboard measuring 4 meters by 5 meters is to be turned into an open box by cutting squares measuring X centimeters from each of the 4 corners of the rectangle as shown. The sides of the box are then folded up to form the open box. We want to show for part A that the volume of the box is given by this equation here. So the first thing we need to do is remember that the volume of a rectangular prism is equal to the length times the width times the height. So for our box, we have the height is equal to X. We then have the length of the box, which might sit here as being 5 meters, and then we subtract 2x from both sides because we cut X centimeters out from each of the corners, which means that the length is 5 minus 2x. And this here may be the width of the box, which would be 4 subtract 2x. So with that in mind, the volume is equal to the length, which is 5 minus 2x, times the width, which is 4 minus 2x, times the height, which is simply x. Expanding that out, we get the volume is equal to, and 5 times 4 is 20, then we have minus 10x, then we have minus 8x, and then we have plus 4x squared, and all of that is still multiplied by x. When we simplify that and expand the x through, we find that v of x is equal to 4x to the power of 3 minus 18x to the power of 2, and that's from the minus 10x and minus 8x combining. And then we have plus 20x. So we've shown that that's the volume of this open box. For part B, we want to state the practical domain of the function v of x. So if you think back to the lengths and widths of the box, we need 4 minus 2x to stay greater than 0. So when we solve this, we need x to be less than 2. As x is a length, we know that it must also be greater than 0. So the practical domain is x is an element of 0 not included to 2 not included in interval notation. For part C, we want to determine the volume of the box when x is 0.25. So that's the same as evaluating v of 0.25. We can use the CAS calculator to assist us in answering many of these questions. To do this, click on the main menu. Next, we want to define the function v of x. So we're going to type in 4x to the power of 3 minus 18x to the power of 2 plus 20x. Then we're going to highlight that and go interactive define. And we can set the function name to be v. If we go into ABC, very important you use ABC, not variables. We can click caps v, and then we can leave the variable as x and press OK, and we have v of x defined. We can now drag down the v of x, and to find the volume when x is 0.25, we just put 0.25 in here and press execute. So from the calculator, this is equal to 63 divided by 16 meters cubed. For part D, we want to state the values of x for which the box will have a volume greater than or equal to 6 meters cubed. So what we want to do is solve v of x is greater than or equal to 6. Once again, we can use the CAS calculator to help us solve an inequality. So we want v of x. If we click keyboard and math 3, we can find when v of x is greater than or equal to 6. We can highlight this and go interactive, equation inequality, solve for x. Using the output of the CAS calculator and our knowledge that the domain is between 0 and 2, both not included, the values of x that give a volume greater than or equal to 6 lie over the interval 1/2 to 1, both included. For part E, we want to sketch the graph of v of x over its practical domain. We also need to clearly label any endpoints, axial intercepts, and turning points with their coordinates correct to 2 decimal places. To graph v of x on the calculator, click on the graph icon, and next you just need to drag v of x down onto the graph screen. And this will sketch the cubic graph, and now we need to manually resize the screen so that we can see everything that we want to. So press the 4 arrows, and we can set the x minimum. We might just set it to be -1, and the x maximum to be 3, so that includes all of the practical domain and a little bit more. Then the y minimum we might set to be -5, and the Y maximum we might set to be 10. And pressing OK, you can see we've got a reasonable amount of the graph sketched here, so that we can use that to help us sketch v of x. Using analysis gsolve and root, we can find the x-intercepts, which are at 0, 0, which we can lock on by pressing execute, and at 2, 0, which we can press execute to also lock that onto the graph. Anything beyond that's outside the practical domain, so we don't need to worry about it. And now we can go analysis gsolve max to find the maximum turning point. And hitting execute will lock that onto the graph for us. So from the CAS calculator, the shape of the graph is something like this. At x is 0, the volume is also 0, and we use an open dot here because that point is excluded. Similarly, at x equals 2, we have a volume of 0, and that point is also excluded. The maximum volume occurs when x is 0.74, and that gives a volume of 6.56 meters cubed, and we state that correct to 2 decimal places. For part F, we're asked to determine the maximum volume that the box can have, stating our answer correct to 2 decimal places. So using the graph above that we generated on the CAS calculator, we can see that the maximum volume is 6.56 meters cubed. So the answer is 6.56 meters cubed is the maximum volume, and this occurs when x is equal to 0.74 meters.